Electron configuration. So explain the atom according to the quantum mechanical model. So the last time that we talked about atomic structure, we talked about the Bohr model. So in the Bohr model, there are orbits that are different distances from the nucleus, and electrons travel along this path. The quantum mechanical model is more accurate. We still have energy levels, but the electrons are not in neat circular orbits around the nucleus. Instead, the quantum mechanical model defines the location of an electron based on probability. So if you can imagine that there was a fly flying around the room, we could track the motion of this fly and use that data to write a math equation that would describe the fly's position in the classroom at any given time. And if we collected a lot of data, we might even be able to predict where the fly might be half a second into the future. So we do the same thing with electrons. We can write a really complicated math equation for the electrons in an atom. And when we do that, when we solve those really complicated equations, the solution is a three-dimensional shape, and we call that an atomic orbital. So atomic orbital is a 3D cloud of electrons moving around the nucleus. And that cloud is going to be denser where electrons are more likely to be found. Now we name these clouds, these shapes, we name them S, P, D, and F. So I can't really tell you where exactly within that 3D moving cloud the electron is, but I can tell you where it is most likely to be within that electron cloud. So orbits are what we had in the Bohr model. These are the paths in which electrons travel. And according to the Bohr model, electrons move between these energy levels by absorbing or emitting energy. And sometimes that energy is in the form of visible light, like you saw in your flame test lab. So that is still accurate. We still have energy levels, but they're not these neat circular orbits or paths around the nucleus. Instead, we have orbitals. So these are the 3D clouds where electrons are likely to be found. So electrons still have energy levels and they still move between them, but those energy levels are instead in these orbitals, these 3D clouds of electrons. So how does the electron configuration relate to the arrangement of electrons in atoms? So think of electron configuration as an address for each electron within an atom. So that address needs to show the orbital and the energy level that that electron is in. So for example, here is the electron configuration for helium. So the 1 here is the energy level, the S is the shape or name of orbital, and this 2 is telling me how many electrons are in that energy level and in that orbital. So if this were an address, you could think of this as 2 electrons live on First Street in an S-shaped house. So I want you to go ahead and take a minute to pause and color code your periodic table. Make sure that helium over here is the same color as hydrogen. And go ahead and take a minute to color these in and label them. Return here whenever you are ready to continue. Okay, so now we want to write the electron configuration of magnesium. So magnesium is Mg, and that's atomic number 12, which means that magnesium has 12 valence electrons. So for each of those 12 electrons, we need to indicate an energy level, a shape, and how many electrons are present. So when you do electron configuration, you always start at the beginning with hydrogen. So first let's talk about the energy level. The energy level is the same as the row on the periodic table. So hydrogen would be energy level 1. And the shape of hydrogen is S. So we're going to go, this would be 1s1, 1s2. Every time you get to the end of a section, write down what you have. Okay. So now we're going to come down here to the next row. So lithium would be 2s1. Beryllium is 2s2. Now we're going to come over here. So we're still in the second row. We're still in the second energy level, but now I am in the P block. So this would be 2p1, 2p2, 2p3, 2p4, 2p5, 2p6. So we're going to write that down. So that's a total of 10 electrons so far. The 2 plus the 2 plus the 6 gives us 10. So now we come down here to our third row. So this would be 3s1. Magnesium would be 3s2. So this is the complete configuration for the electrons in magnesium. So there are 2 electrons that live in an S-shaped house on 1st Street. There are 2 electrons in an S-shaped house and 6 in a P-shaped house on 2nd Street. And on the 3rd Street, we have a pair of electrons living in an S-shaped house. So this time we want to do iron. So iron is Fe with 26 protons. This means that it has 26 electrons, and we need to give the address for each of those electrons. So we're always going to start at the beginning with hydrogen. So hydrogen is going to be 1s1, helium is 1s2. We come down to the next row, 2s1, 2s2. Now we're going to come across, so we're still in the second energy level, but now we're in the P block. So this would be 2p1, 2p2, 2p3, 2p4, 2p5, 2p6. Now we're going to come down to sodium. So this would be the third energy level. The shape is S. So sodium would be 3s1 and magnesium is 3s2. Now we're going to come over to here. Remember, we want to keep going until we get to 26 electrons, which is iron. So we are in the third energy level, and now we're back into the P block. So this would be 3p1, 3p2, 3p3, 3p4, 3p5, 3p6. Now we're going to come down to here. Potassium is going to be 4s1. Calcium is 4s2. Now we're getting into the D block here. And there's kind of an exception to the D block, and the D block actually starts with 3D. So I know that you want to say that this is 4D because it's in the 4th row. The D block is a little bit more stable than the S and P block, so it starts at a slightly lower energy level. So instead of starting at 3D, it's going to start, or rather, instead of starting at 4D, it will start at 3D. Remember that these guys are inserted into here on the periodic table, and the F block would be behind by 2. So I know you want to say this is 6F. This would actually be 4F and 5F. So 3D, we have 3D1, 3D2, 3D3, 3D4, 3D5, 3D6. So here's the electron configuration for iron. Next, we want to do krypton. So that's 36 electrons. So when you're dealing with elements that have a lot of electrons, there is a shortcut that we can use instead of writing out the complete configuration. So to use the shortcut, we're going to look at the last noble gas before krypton. Remember that noble gases are going to be in column 18 of the periodic table. So the last noble gas before krypton is argon. So rather than writing out those first 18 electrons, I'm just going to put argon into a square bracket here, and then start with calcium at 4s1, or potassium 4s1, calcium 4s2. Then I've got 3d10. Remember that this D block is behind by 1. So that's 3d instead of 4d. And then I've got 4p, 1, 2, 3, 4, 5, 6, 4p6. So rather than writing out the first 18 electrons, rather than writing out 1s2, 2s2, 2p6, 3s2, 3p6, rather than writing all those 18 electrons out, we can just start with the last noble gas before the element. And it has to be a noble gas. Reason being, noble gases are in that last column, which means that that orbital will be full. So we start at the last complete full orbital, which in this case would be argon with 3p6. Next, we're looking at rubidium, which is 37 here. So I can use my shortcut and go to the last noble gas before rubidium, which is krypton. So for rubidium, I'm going to put krypton in square brackets. So that means the electron configuration for the first 36 electrons. And then I've got one more here to get to 37. So that's going to be 5s1. So now let's take a look at calcium and calcium plus 2. So I want you to pause the video and go ahead and write the electron configuration for just calcium. Go ahead and do that now. So calcium has a total of 20 electrons. So its configuration is going to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Now we call the highest occupied energy level, we call that the valence shell, or the valence energy level. So the highest energy level for calcium is 4, and it's got a total of 2 electrons in that highest energy level. That's important because it's the valence electrons that are involved in chemical bonds. So my first energy level has 2 electrons in it. My second energy level has a total of 8. There's 2 in S and 6 in P, so that gives us a total of 8. Same thing in the third energy level, and then we have 2 in our outermost energy level. So let's think about calcium plus 2. How is that different from regular calcium? So remember that this is a cation, which means that we have lost electrons. And in this case, we've lost 2 electrons to form a plus 2 charge. So go ahead and try to write the configuration for calcium plus 2, keeping in mind that you're going to lose those outermost electrons. So the electron configuration for normal calcium is this. But this is calcium plus 2, and we have lost these outermost valence electrons. So now my highest energy level is energy level 3, and that has a total of 8 electrons in it. So my first energy level has 2, my second has 8, my third has 8. All right, let's think about sulfur and sulfur minus 2. So go ahead and pause the video and write the electron configuration for sulfur. So sulfur has a total of 16 valence electrons. So 1s2, we've got 2 in the first energy level, 8 in the second, and then 6 in the third. So our highest energy level is energy level 3, and that has a total of 2 plus 4. That makes 6 valence electrons. So now let's think about S minus 2. So minus 2 here means that this is an anion, and we have gained 2 electrons. So think about where you would add those 2 electrons and go ahead and try to write the electron configuration for sulfur -2. So sulfur -2 is going to have the same configuration as sulfur, but we have 2 more valence electrons here. So instead of 3p4, we have 3p6. My highest energy level is energy level 3, and it has a total of 8 valence electrons. 2 in the first energy level, 8 in the second, and 8 in the third.